In today's video, we are going to continue our discussion of polynomial functions. So in one of the earlier videos, we discussed the definition of a polynomial, and we looked for the degree and lead coefficient. We're going to look at a little bit more vocabulary today, and we're going to see what do that degree and leading coefficient mean about the graph of the polynomial. So how do they affect the graph? We're not going to actually graph, but we're going to look at how they affect the graph. So we're going to start with a little bit of definitions again. A polynomial in one variable is an expression of the form a to the n x to the n plus a times x to the n minus 1, a2x squared, a1x, a0, where all those constants are real numbers and n is a non-negative integer. Okay, what that means is our exponents are positive, they're whole numbers, including 0, and we have constants out in front of them. So a to the n is just a constant. A polynomial is written in standard form when the values of the exponents are in descending order. We did that with synthetic division. We made sure we always had our highest exponent first, all the way down to our lowest exponent. The degree of the polynomial, we've talked about this before, is the value of the greatest exponent. And then hopefully we can get this next one. I gave you a sneak peek in the previous video. The coefficient of the first term of the polynomial, when it is in standard form, is called the leading coefficient. Okay, so then we're going to go on a little bit and see what that means in some of these next examples. Like we did before, we're going to have to be able to identify a polynomial, find the degree, and find the lead coefficient. Example 1, state the degree of and leading coefficient of each polynomial. If it is not a polynomial, explain why. If it's not a polynomial in one variable, that is. Okay, if we look at the first one, we have a degree of 2, or an exponent of 2, an exponent of 3. At the end, this is like x to the 0. So, is this a polynomial? Well, are all of our exponents 0 or positive? Yes. Are they all whole numbers? Yes. Are we dividing by any variables? No. So we would say, yes, this is a polynomial. If we're looking for the degree, it's the highest exponent, which in this case is 3. And then our leading coefficient, be careful here, it's not the coefficient out in front. It's the coefficient that's out in front of the term with the highest degree, which is actually the middle one. So our lead coefficient here is 1. It's 1. Okay, I want you to try the next one. So pause the video. Ask yourself first, is this a polynomial, yes or no? If it is, find the degree and lead coefficient. Okay, is this a polynomial of one variable? No. This is not a polynomial of one variable because it has two variables. So we've talked about this one before. It is a polynomial, but not in one variable. That's the issue. Okay, if that's confusing, there is an extra example at the end that we can look at together. Moving on, we're going to talk about evaluating polynomial functions. So this, I believe you have seen before. Find r of -2 and r of 3 for each function. So let's review this notation. What's in parentheses is what you're plugging in for x. So r of -2 is saying plug in -2 for x. So r of -2, any place I see an x, I'm going to plug in a -2. Being careful here, I have -2 squared, so that's like x squared, plus 2. In place of x, I'm going to put a negative 2. Let's make sure we follow order of operations. On that first term, the exponent comes first. So negative 2 squared is 4, then a negative. 2 times negative 2 is negative 4, and then minus 5. Negative 4 add negative 4 is negative 8. Negative 8 minus 5 is negative 13. So that's it. That notation is asking you what is the output when the input is negative 2. We are also finding r of 3, which means you're plugging in this time 3 for x. So I have negative x squared plus 2 times x minus 5. So 3 squared is 9, then it becomes negative. 2 times 3 is 6, minus 5. If we combine all of that, negative 9 add 6 is negative 3. Negative 3 subtract 5 is negative 8. Okay, you are going to try the next one. You are again finding r of negative 2 and r of 3 for the polynomial written. Pause the video, try those on your own, or try this problem on your own, and then come back, please. Okay, hopefully that went well. We will go over that next time you are in class. We're going to go to the next page to do one more example with evaluating polynomials. In this next example, we are still evaluating. A little bit of different notation though. In parentheses, we have negative 3a. That's what's going in for x. Because our input is in terms of a, our answer, or our output, is going to be in terms of a as well. So if we try to find p of negative 3a, we have 2 times x squared plus 1. Now, in place of this x, we're putting negative 3a. So order of operations tells us to do that exponent first. Negative 3 squared is 9, and then a squared. So we get 18a squared plus 1. And that's it. So a few things for me to point out real quick to you. First of all, we said since our input is in terms of a, our output is going to be in terms of a also. I also want to point out you have a p here and a p here. That tells you what function to use. So p of negative 3a tells you to use equation p. If there was an f there, you would be using equation f instead. So hopefully that makes sense. We're going to move on and look at the next topic for us, which is end behavior. So let's start with, what does end behavior mean? End behavior is, the behavior of the graph of f of x as x approaches positive infinity and negative infinity. So we are looking at what happens to the graph when we go far to the left and far to the right. It's related to domain and range in that way. You determine end behavior using two different pieces of information. And this should make sense. On the first page with a polynomial, we looked at the degree. Specifically, you care, is the degree even or odd? So the specific number doesn't really matter. What matters is whether the degree is even or odd. And then the leading coefficient. What you care about is that leading coefficient positive or negative? Okay, so we're going to look at end behavior in two different ways. First one is when you are already given a graph. And then we're going to look at end behavior when you are given an equation. So let's look at these examples we see. For each graph, we're going to talk about the end behavior. We're going to determine whether this is an even or an odd, and state the real number of zeros. So this first graph here, talking about the end behavior. As x goes to positive infinity is the right. So as x goes to the right, what's happening to y? So that's this way. As x goes to the right, we see the graph is going up, so it's going to positive infinity. Okay, so then this bottom one, as x goes to negative infinity, that's going to the left. What happens to y? Well, as x goes to the left, the graph goes down, so that's negative infinity. Okay, we need to figure out if this is even or odd. Here's how you can tell. In an even degree function, the graph starts and ends in the same direction. So the graph will start and end up or start and end down. Even, think of twins. Odd, the graph will start and end in different directions. Okay, so in this case, we see the graph starts down, ends up. Different directions means this function has to be odd. Zeros is when the graph crosses the x-axis. So on our graph, our line crosses the x-axis once. So there is one real zero. Okay, we're going to try the next one. As x goes to positive infinity, so again, the positive direction is right. What happens to the graph? So as we go right, the graph is going down. It's going to negative infinity. As x goes to negative infinity, so that's this way, the graph still goes down. Okay, so degree, again, I want to know if this is even or odd. Well, this graph is twinning, starting and ending the same, which means the degree is even. Then if we're looking for the zeros, we're looking for every time that the graph crosses the x-axis. That's here, 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 and here. For number of zeros, we actually have 4 of them. Okay, this next example I would like you to try on your own, please. Pause the video, come up with the end behavior, the degree, and the number of zeros. Okay, I hope that one went well for you. We will go over that one next time we are in class together. Let's flip to the next page. Last thing that we need to talk about is end behavior using an equation. Okay, so end behavior, we're describing again. This time we don't have a graph though, so we're going to need to draw a graph. Here's what we know. We know the degree. So our degree is odd, right? Highest exponent is odd, which means we're going to start and end in different directions. Our lead coefficient is positive. Here's why that matters. The lead coefficient tells us how the graph ends, how it ends. So positive means we are ending up. We also know because it's odd, we're going in different directions. So this graphically is how our graph would start and end. So this is how we're going to do our end behavior then. As x goes in the positive direction this way, f of x goes to positive infinity. As x goes to negative infinity, the negative direction, the graph goes down. Okay, you are going to try the next one. What I want you to do is figure out the degree. Is it even or odd? And then the lead coefficient. Is it positive or negative? You're then going to need to draw yourself a graph. Remember, the degree, the even or odd, tells you do they start and end the same or start and end differently. And then the lead coefficient will tell you how you end. So pause the video, try this one on your own, please. Okay, I'm going to help you with this one a little bit. If we look at the degree, highest exponent, make sure you look at all the terms. In this case, the highest exponent is 7, which means we have an odd degree. Again, different directions. Leading coefficient is negative, which means we are ending down. When you come to class, we will go over the rest of this problem. There are a few extra examples which are optional for you. If you feel that you have this content down well and you understand what you are doing, then you are free to go. Make sure you've tried the extra examples and turned in your notes. If you want to stay on for a few extra examples, please do so. For the first example, I want to know, is this a polynomial? Yes or no? And then we're going to find the degree and lead coefficient. So is this a polynomial? Yes, it is. We don't have any negative exponents. We only have one variable. We're not dividing by any variables. So yes, this is a polynomial. If we want to look for our degree and our lead coefficient, highest power is 8. Our lead coefficient then is -4. It's not 3. It's -4. Because remember, you want to think of this being in standard form. So if we wanted to put this in standard form, we would have -4 x to the 8th plus 3 x to the 4th plus 10x. For part B, we're finding t of a squared. So again, that t just means we're using equation t. A squared is what's going in for x. Okay, so we have -x squared negative. Instead of x, we're putting a squared plus 7 times x minus 1. So again, a squared just went in for x. First, we have a squared squared. So we got to ask ourselves, what do we do with those exponents? We're going to multiply them. So that's a to the 4th with a negative plus 7a squared minus 1. And then we're done. Part C, we are describing the end behavior. First thing I'm going to do is I'm going to write this in standard form. So I have the highest power first. Two things we got to look for, the degree and lead coefficient. In this case, my degree is even. So again, I don't care that it's a 2. All I care about is that it's even. And my lead coefficient is negative. Okay, what does that tell us? Lead coefficient is always how we end. Even means that they're going to start, both sides are going to start and end the same. Now we're ready to fill out our end behavior. As x goes to positive infinity, that's this way, my graph goes down. As x goes to negative infinity, my graph also goes down. So hopefully that clarified some of the concept in today's video. If you have any questions, please write them down, come to office hours, or send me an email.